Okay, once again, good morning everybody. The plan for today is to start from this presentation, which is about, as you can see, earth retaining structures. So we will start today dealing with geotechnical works and with their at least preliminary design, putting together everything we have already seen during this course. Now, this presentation enables me to talk about the earth pressure criteria, earth pressure theory that we will use for the understanding of the mechanism related to the bearing capacity of shallow foundations. So, despite you see this title, today we will not talk about earth retaining structures, which is something that Professor Marchi will deal with. The topic of today is about foundations, shallow foundation. We start defining what is the shallow foundation is and how we can approach the design of a shallow foundation starting from bearing capacity calculation. In order to do so, we have to remind you, because basically I am sure that all of you in your bachelor have already seen this basic theory, but we need to remind you the earth pressure theory, at least the theory proposed by Rankin. Okay, so this presentation is essentially to present you with the limit lateral earth pressure, which is the bottom point, according to Rankin's theory. And I will just show you the first slide relating to the types of earth retaining structures, just to let you know what we are after. Okay, so an earth retaining structure is a structure which is designed to support some soil behind it. As you can see, the very simple basic structure is the one that you can see at the top left side of this slide. This is what is called a gravity structure, so a rather heavy structure. In fact, it is called gravity retaining wall because it will prevent sliding away because of the earth pressure, which you can see named P in the figure, using its gravity, its weight. So the more it weighs, the better it is, the more stable it is. Now, of course, once you move to high, higher soil to support behind it, then it becomes difficult to use this kind of structure. Another possible shape is what you see in the top right figure. They are, and of course, this is a bit more slender than the other one. So this is also subjected to strains inside it. So you have to put steel. So you have to design it as a proper structure. We in geotechnical engineering we mainly we are mainly concerned with the design of the actions on this type of structure. Okay, the design from a structural point of view A gravity structure like the one on the left is rather crude, is not typically, you don't have steel inside, but we have to separate the design from the geotechnical and the structural point of view. Of course, they are all part of the same design, but first we have to define actions on the structure. Once you have defined all the actions, then you can design it as a structural element. And of course, in this case, the geotechnical part, which is, if you want, the most critical part, is to define that the force P, which is the force that the soil behind the structure acts on the structure itself. Okay, now there are many types of earth retaining structures, both gravity, which can be very high, as you can see, and of other types, and these are embedded structure, which work in a totally different way. But as I said, this is not the topic of today, so I'm skipping these slides, and Professor Macchi will come back again defining all these types of structure. Okay, now as I said, the design of a retaining wall from the geotechnical point of view requires to define that P. P is the resultant of all the lateral, the horizontal stresses provided by the soil behind the wall. Okay. Now the wall, if you can see, that wall as it is somehow in place of a possible slope, other soil, which would allow that slope to be stable. If you remove parts of the soil, if you have a sort of vertical slope, then typically the soil is not able to self-sustain. And you need a structure providing some support to the soil behind. Now, how much is this support? This depends on how much is the horizontal pressure from the soil behind. So basically, if you think, and once again we're not going to the detail of the design of this structure, but basically you see you have an horizontal force which can be implied by an angle delta, because you might have some friction between the wall and the soil, so it will not be exactly horizontal, but basically you have something pushing against the wall, and the wall which is resisting with a vertical weight. Now, of course, you have a horizontal force and the vertical force, which is the weight. How can you guarantee equilibrium, the horizontal equilibrium? Because this will develop some friction at the base of the wall. You see that force H, which is proportional to the weight W. Okay, so in this way you can guarantee the equilibrium. So what we have to do is essentially to define, to derive, to understand first of all why the soil is pushing against the wall, and how can we define the value of such earth pressure P, PA, which is then made of two components, vertical and horizontal, PV and pH. So I'm skipping this, the verification, which are part of the design, and we now go to the calculation of the lateral earth thrust. Okay, so we will make use of two theories, essentially classical theories, nothing new, as you can see from the dates of the relative authors who proposed them, ranking in the 19th century, and Coulomb, of course, was really the very first to study the stability of retaining walls due to military reasons at his times, But today we will focus only on the ranking theory, and we, as you can see, it is based on very simple assumptions, not always verified, but that can be used to as a preliminary idea of what this horizontal earth pressure comes from. So remember, there is no adhesion or friction between the wall and the soil, and we have just mentioned that this friction is there, can be there, and so the horizontal force is not inclined by an angle delta, as we have just seen, but according to Rankine, this is perfectly horizontal because there is no delta, no friction between the wall and the soil. Now, of course, this is a rather crude assumption. Typically, there is friction. The soil is a frictional material, so between a wall which is made of concrete and the soil, you always have friction. But then this is an assumption which is somehow a conservative assumption. Okay, neglecting the friction provides you a conservative design. Vertical wall can be inclined. In this case, it's vertical. Failure occurs as a sliding wedge along an assumed failure plane defined by the angle, shear strength angle on the soil phi, and the lateral pressure varies linearly with the depth, and the resultant pressure is located 1/3 of the height above the base of the wall in case of a cohesionless soil. Now, and the resultant force is parallel to the backfill surface. So, as you see, many assumptions. Where does this assumption come from? Why we have to, in order to apply this theory, we have to introduce these assumptions. Now, basically, the ranking theory for the design of retaining walls comes from the ranking limiting states of stress. And this is what I referred earlier on that you should be familiar, because this is typically something which is dealt with in the Bachelor of Soil Mechanics course. It is immediately after you have defined the existence of limit equilibrium lines, which is defined, for example, by the Moore-Coulomb criterion, which as you see, if it is expressed in terms of effective stress analysis, and for a cohesionless soil, it says basically that the maximum tangential stress is proportional to the normal effective stress to the failure plane times tangent of phi, and where phi is the angle that you can see highlighted here in the Moore-Coulomb plane. Now, if you start in a very simple situation, which is enough space, okay, like the one you have already considered, so you are in a sort of one-dimensional condition, and you want to define what is the stress at a depth z from your ground surface. Okay, so let's assume that this is your ground surface. You have a soil element at the depth z. Now we know that in this very simplified situation, still realistic and possible, your vertical stress is not only statically determined from the vertical equilibrium, for example, gamma z, but it is also a principal stress. Okay, so we know that this is your principal stress. This can be sigma 1 or sigma 3, depending if it is the major or the minor principal stress, but we know that in this situation, this is a principal stress. In the same way, we have the horizontal stress, which will be the other principal stress. So let's say sigma 3, if the horizontal is less than the vertical stress. Now, the horizontal stress, we know it is not statically determined. So it can be any value. It can be any value because you can guarantee the horizontal equilibrium for any value of the horizontal stress. And we have, and if you think that this is a fully saturated soil, so we have to consider we have to separate, distinguish between the total and effective stresses. Let's always refer to effective stresses. So let's put an apex to all stresses in case there is a difference between effective and total stresses. Now, we have said, also at the beginning of this course, that the horizontal stress can be expressed as a function of an earth pressure coefficient K0. Okay? So this is a different way to express the relationship between vertical and horizontal stress. Okay? This is valid in terms of effective stresses. So you have effective stress here, effective stress here. So you can define K0 as the ratio between sigma H0 and sigma V0, where all this naught refers to initial conditions. Okay? Undisturbed conditions before you build your retaining wall or you apply the load, everything just as initial state. Now, this was called earth pressure coefficient because it is something related to earth pressure, which is what we are talking today. Okay? K0 is therefore the ratio between these two stresses, and it is not possible to determine analytically. We gave an expression, an empirical expression, typically 1 minus the sine of the angle phi. Okay? This is the expression for a normally consolidated soil. Once you have K0 for an over-consolidated soil, then you have your K0 for the normally consolidated soil times OCR elevated to an exponent alpha, which is typically around 0.45, 0.5, something less than 1. Okay? Everything is already seen and I hope well known from you. Why I'm reminding this? Because we are in this situation from the stress state point of view. We have the vertical stress, effective vertical stress, which is a principal stress. So the point lies on the sigma axis. You might have an horizontal stress in initial conditions, which is not statically determined. So it can be any point. It can be on the left-hand side, if K0 is less than 1. It can be on the other side, if K0 becomes greater than 1. Is it possible to have a K0 greater than 1? Yes, because this is certainly less than 1. This is a positive number, so this is definitely less than 1. But if you multiply by a positive number elevated to an exponent, this becomes greater and greater with OCR, and this can become greater than 1. So this means that your state stress goes on the other side, and you have an horizontal stress which is higher than the vertical stress, and you have, in this case, the horizontal stress would become the sigma 1, and the vertical stress becomes sigma 3. Okay, so you have an inversion of the principal stresses. But still, the initial stress state is represented by a Mohr circle, which lies like in the left-hand side picture. As I said, the horizontal stress is not statically determined, can be any value, but is limited by the limit lines, which is defined by the Mohr-Coulomb criterion. So you can see that this circle can be any circle lying below the limit line. At limit, you have only two circles that are tangent to the limit line, to the Mohr-Coulomb failure criterion, that you can see on the right-hand side. So you have two limit conditions. once you define your vertical stress, and the vertical stress is defined by vertical equilibrium, then the condition of being tangent to the limit line, makes the two circles statically determined. There are only two circles going through your vertical stress, sigma dash V naught, that are tangent to that line. One with the horizontal stress smaller than the vertical stress, the other one with an horizontal stress greater than the vertical stress. Okay? So you have two circles statically determined, only two, that are tangent to the line and go through your vertical stress. These two conditions are called active condition. If you have the smaller circle, the one with the horizontal stress smaller than the vertical stress, and passive condition, which is the other one, the larger, more circle with the horizontal stress greater than the vertical stress. Now, how can you get to this line? So let's try to think of a possible load path, because last time we discussed about load path. Okay, so let's assume that you have your Moore circle and you start from an initial condition, let's say like that. So you have your vertical stress and you have your horizontal stress, and somehow you have your limit line inclined by phi. Okay, this is your initial conditions defined like that, and as I said, unless you know K naught, you don't know this Moore circle. Let's assume that you know K naught, you know the horizontal stress, this is your initial point. Now, how can you get to these two limit conditions? In the first case, you can keep constant the vertical stress, and you can reduce the horizontal stress. Okay, so you can have something like that. You see that if you keep constant one principal stress, and even if you reduce the other principal stress, you make a Moore circle greater. So you increase also the associated tangential stresses. And you can reduce your horizontal stress until you get to your limit circle. And in that case, we have defined this sigma A, because this is your active stress state condition. Okay, so in order to get to this, you have to reduce the horizontal stress, keeping constant the vertical stress. You are in this condition, and you have to keep constant this. So let's assume that it is the depth is always z, and you reduce the horizontal stress. It is, if you think our S prime T prime plane of our load path that we discussed last week, we are going in that direction. Okay, this is A to D, and we discussed this possible load path, reducing the mean stress, so unloading the soil. And if you remember, this situation was exactly related to the design of a retaining wall. So we are back to what we are discussing today. Now, what is the other possible situation? As I said, you start from this, and you get to this limit circle, which is your active. You might have a different load path, still keeping constant the vertical stress. You increase your horizontal stress. So let's assume that we push against the soil element, both sides. So we compress the soil element and we increase the horizontal stress. So we start from here, we reduce the circle because we increase the horizontal stress, then we go the other side and we keep increasing the horizontal stress once again. Okay, so in this case, if we increase the horizontal stress in this direction, as I said, once the horizontal stress goes on the other side, you have inversion of the principal stresses. And you can increase this, see, circle become very great until you get to your circle, which is tangential to your limit line. Okay? And this is what we call the passive condition. So you have two, if you look at the right-hand side, you have two possible limit conditions, but they are really different. Okay, if you look at this slide, you say, well, okay, if you look at that, you have the two possible circles, they are statically determined, but you can get according to completely different load path. Okay. Once is going this direction, this is what we call the active pressure. So the active pressure is referred to this circle, and we call the horizontal stress sigma dash A, and you can go increasing the horizontal stress, that if you remember from last time is exactly going the opposite direction and going towards the other quadrant of your plane. And so this is you get to the passive pressure, and the passive pressure, the limit passive pressure refers to this big Mohr circle, and the horizontal stress is called the passive pressure. So I'm stressing this because if you look at that plot at the right bottom side of your slide, the two conditions look equivalent. Okay, you have two Mohr circles, one side and one with the horizontal stress on the other side, but they correspond to totally different situations. Or let's say one is the opposite of the other. What is relevant for our gravity retaining wall? If you have let me see if I have a picture here. Okay, if you consider that you, in this situation of a half space, everything is similar, vertical and horizontal stresses are principal because everything is symmetric in these conditions. So now let's assume that you remove, you have an imaginary wall that will substitute this soil. So let's assume that you remove this soil and you substitute this soil with an imaginary wall which is able to provide the same initial horizontal stress. Okay? So in this case, you have exactly the same stress state in this soil element, because you have just removed the soil but put a wall inside. A wall able, perfectly vertical, no friction, exactly the same assumptions we have introduced in the previous slide. Now you have a wall, and this wall can move. Why this wall move? Because you have an horizontal stress acting here against, so the wall is acting against the soil, and the soil, for equilibrium, is acting against the wall. So you have a horizontal stress here, horizontal stress here. You have this sigma horizontal stress which acts all along the wall height. Okay, and if you think about this, will sigma h will increase with linearly with z, because the vertical stress increases linearly with z. The horizontal stress is proportional, and so is also increasing. So you will have a plot of your horizontal stress which goes like that, and the resultant, as we mentioned before, of a triangle is applied at 1/3 from the bottom of your wall. So you have this situation, and if this wall is not prevented to move, so if this wall can move, the wall will move. And if the wall moves, the soil will expand and will reduce the horizontal stress, keeping constant the vertical stress. So we are exactly in this load path situation. You go from A to D because you are keeping constant the vertical stress and reducing the horizontal stress. Now, in reality, the wall will tend to rotate according to a pinpoint at the base. According to Rankine, this wall moves perfectly homogeneously horizontally, so there is no rotation along the base. But you can see that that situation, that black wall can represent a sort of a gravity retaining wall or any retaining structures. Essentially, when it moves laterally, it will tend to reduce the horizontal stress. Now, the stress state will not be exactly as in the rank according to ranking assumptions, but we can think that in the first instance, this wall is moving homogeneously laterally and reducing the horizontal stress. So you see, the assumption of the ranking theory are recalled here. No friction between wall and soil, and you have failure occurring according to that the planes. Why exactly those the planes we will see in a minute, but you can see that you can understand why the soil behind the wall can reach failure. Because you get to this situation, to the final circle. So essentially, you move the soil laterally, you reduce the horizontal stress, so you are now increasing the size of your bore circle. Once you get to your limit, you cannot reduce further the horizontal stress. So this is the limit stress. And the limit stress is what acts against the wall just before failure. Now, you can still continue moving your wall, but the soil at that stage is failed. And it's failed and will move along these planes. Okay? So, you reduce the horizontal stress until you reach failure. And your active conditions, this active pressure, that we know how much it is, because this is statically determined. It's no longer like this equation of K naught, because we know this, we know this, we know the tangential condition, and so we can determine this, and we will see now in a minute. So we can define these active conditions as conditions at failure, when the wall has moved laterally until it gets to failure. Okay, so far? Now notice that if we consider this stress state, this plot, the resultant, as a possible PA, what we call the PA, the active pressure, in the first slide this morning, if we design this wall with this PA, we are essentially designing our wall with the minimum horizontal stress. So with the minimum force that can act on the wall. And this doesn't sound a conservative assumption. You typically tend to design with the maximum possible horizontal stress. So which is the maximum? This one. So we should, in principle, if you don't understand the mechanism, you say, well, I will get the maximum horizontal stress. Because you can have a situation like that with a passive condition, and so I will say, no, I will use the passive, so I want to be conservative. Now, two things. If you have to design a wall like that with a passive, you will never be able to design a wall supporting a passive pressure. But this is not a good reason. If it is conservative, you have to be conservative. So you have to think of something different. But the other point, crucial point, is that this is not possible in this situation. Because in order to get to this circle, you have to push against the soil. You have to increase the horizontal stress, compressing the soil. And this is not a possible mechanism. If you remove this soil, the worst it can go is this stays where it is. So the maximum possible pressure against this wall is the initial state, the at-rest pressure. This is the maximum. Once this wall starts moving laterally, expanding the soil, the horizontal stress will tend to reduce until it gets the minimum. So you say, well, okay, so my maximum is the initial stress state, and I will use that. And in fact, if this possible wall is prevented to move laterally, you have to consider lateral stress. There are possible walls in which you have let's say, an excavation like that, and you have some structural elements like that. So this is a very rigid structure. Now you will see when we will design retaining structures, and this is totally prevented to move. In that case, you cannot consider this one, which is the minimum, but you have to consider the horizontal, the initial stress state. So all what I'm going to say is that typically retaining walls, especially gravity retaining walls, are designed with the active pressure. And this is what you typically know and learn from your bachelor courses. So what's the big deal with it? Use the active pressure. Well, the active pressure, behind this assumption, you have to allow your wall to move to expand until it gets to this condition. Because the active pressure is the minimum force acting on the wall. So you can design using the minimum force as long as you allow the wall to move sideways enough to get to the active pressure. So never forget this. Typically, if you design a gravity retaining wall, like the ones we have seen at the beginning, the wall will, just a very small movement of the gravity wall is enough to reduce to your stress state from here to here. Only a small movement. And we typically allow that at failure in order to be able to design the wall with a minimum force and not over-design your wall. Okay? But never forget that at the base, the basic assumption to use the active pressure is that you are using the minimum for horizontal force that the soil is able to act on your wall. This is a very important point. Now, in fact, if you look on the other side, now we will derive this expression of the active pressure and of the active earth pressure coefficient in the following slide. But let's go on the other side. You see, in order to get in the passive zone, in order to get to this circle, you have to push against the soil. So this will never happen for a retaining wall. When can this happen? Just to remind you, this situation, this passive load path, last week we have seen was, for example, you have a retaining wall, which is not a gravity retaining wall. This is an embedded structure. Okay, this will tend, because this is you have an active pressure here moving the soil, so this will become like that. And if it is true that this goes to active conditions, because this is expanding the soil, the other soil on the other side will be compressed. and so it will react with something increasing the horizontal stress. Now, if we get to the final failure circle, this is not granted, given for granted, but still the load path of the soil here is more like that, whereas the load path of the soil here is more like that. So you see the tricky thing of the soil behavior, that even the basic requirement to know actions acting on the structure. Typically when you study a structure, you know the actions, you know the weight, you know the wind, you might take into account the seismic actions, but it is something, typically for you design a structure, you know the actions. In this case, the actions are determined by the interaction between the structure and the soil. And we have seen last week that, for example, this load path, which was the combination of this unloading because of the excavation and this loading because of the passive load path, even the actions are not known in advance and can become on your design. Remember what we said last week. So this is somehow goes together with what we said last week for the load path. Now, the only thing we are left with is to determine this. What is the amount of this active horizontal stress? What is the active? Because you may define a Ka, an active earth pressure coefficient, which is like that. But you have now. Let me cancel this because otherwise you'll be confused. You have the horizontal active pressure instead of the horizontal at rest pressure divided by sigma d naught, which is exactly the same because the sigma d naught has never changed. Okay, so we have to now define this Ka, or defining this horizontal active pressure, and then we will be able to know this triangular plot, to know the resultant, and to know the force against our gravity retaining wall. So this is what we are going to do right now. This is actually a slide showing that if you have this wall which is moving this way and you have the soil here, this will decrease and this will increase. But this is just thinking of a possible embedded retaining wall like this. Okay, so we have already discussed this, and as I said, Professor Marchi will come again on this presentation. I only want to stop a little bit on this slide, this one, the red one, in which you have the active limit conditions. Okay, let me cancel this. So we are in this situation. Sigma dash and tau. We are in the Moore plane. And you have a straight line, which is our limit line defined by the Moore-Coulomb criterion, that if we assume a cohesionless soil, then we will see that it is can be extended also for a soil, a cohesive soil. But for a cohesionless soil, so no cohesion, the Moore circle is defined, as we said, by sigma dash the tangent of phi dash. And phi is our angle of our straight line. Now we are dealing with this can be any circle tangent in this equation, where you have to know sigma vertical, but this will depend on z. So you can have any circle like that, changing your z, your depth z, and then you have your horizontal sigma a. And you want to know what is the amount of sigma horizontal in this condition. That, as I have just said, is statically determined by this tangential condition. Okay? So, if you think that this is a circle and the radius of a circle is always orthogonal to any tangent. Okay? So we know that this is 90 degrees. And this is phi. So this, we know also this angle, which is 90 minus phi. You can write this, let's say this is the radius of the circle, this is the sigma v naught minus sigma a, which is our horizontal stress, divided by 2. The circle is the diameter, the distance between this and this, divided by 2. But if you consider this rectangular triangle, you can also say that this is this, which is the semi-sum of the two principal stresses. This distance is sigma v naught plus sigma a divided by 2. If you see, this is this distance, and this is multiplied by the sine of phi. Okay, because this is a triangle which is rectangular. Okay, so you can put this in these two different ways, and this, you know, essentially everything of this equation except for sigma a, because you know sigma v naught, which is statically determined, you know phi, which is your limit load, and you solve for sigma a, active pressure. Okay? And this will become a function of phi. Now, if you do all the passages, and I will skip that, you end up with this expression you can find on the top right of your slide. And so you see that your sigma active is a function of phi and a function of sigma v naught. And remember, sigma v naught is, for example, gamma dash z. So is linearly increasing with z. In the same way, the horizontal, sigma a is increasing with z, is linearly increasing with z, times a coefficient which is 1 minus sigma phi. Let's put it here, so otherwise it's too difficult to read on the slide. So if you solve for sigma a, you end up saying that sigma a, active conditions, is 1 minus sine phi divided by plus 1 sine phi times sigma V naught. You call this Ka. And you see, you can write, in fact, sigma A, Ka, sigma V naught. Because Ka is the ratio between the horizontal stress and the vertical stress in active conditions. So this becomes Ka, and this, if you apply trigonometric equivalent formulas, you can write this as square tangent of 45 degrees minus 5 dash divided by 2. This is the same thing, gives you exactly the same value. It's just applying the trigonometric formulas equivalent. So you can express K this way, you can express this way, and clearly, this is less than 1. It is also less than K naught. K naught for normally consolidated soil was 1 minus sine phi. This is divided by something which is greater than 1. So Ka is the minimum earth pressure coefficient that you can think of. You cannot go lower because the soil fails. So you can no longer reduce your Mohr circle. Now you have this expression, and you can know sigma A. Now let me cancel this. Now you have your wall, which was in principle it is a static, is a gravity wall, so it will be much thicker than that. But let's assume that this is our Rankine wall, which is an imaginary wall, and what is the plot of this? Now remember, this increases with Z, so this is linearly increasing, so you have essentially Ka gamma dash Z. And once again, the graph, the trend with depth of your active pressure will be like that, as we drew before. Okay? So this, the slope of this line will be gamma dash times Ka. And being Ka less than 1, this is smaller than the vertical stress. But this is what acts against the wall, and this is why Rankine says the resultant of this is applied at 1/3 of your height h of your wall. This is 1/3 of h. Now, once you get to failure, if you keep moving the wall laterally, the soil reaches this, and the soil will tend to slide, to move along those slip planes. Why those slip planes? Why these slope planes are inclined with the horizontal line of this angle that you can see here, 45 degrees plus 5 divided by 2. Why exactly that angle? Now we can once again go back to this figure and think that you have, this is the pole of your circle, the origin of planes, okay? Because this is the horizontal load which acts along the vertical plane. This is the vertical stress which acts along the horizontal planes. So you can easily determine that the original planes of this Mohr circle at this point. So the failure plane, where you reach failure in these conditions, are represented by this point. Remember, in the Mohr circle, each point represents a specific plane. So if you connect this failure point with the original planes, then you find the angle of your plane. And this angle is exactly 45 degrees plus phi dash divided by 2. Now, either you believe me or we can find it together, which is really just a geometrical thing. We know that this angle is 90 minus phi. You can think of this, and this is this angle, which starts from your circle, is by geometrical theorems that you should go back to your secondary school studies. This angle is twice as much as this angle, because they insist on the same arc of your circle. Okay, so we know that this angle is 90 minus phi divided by 2. Okay? Now, any triangle which is inscribed in a circle with its diameter is another rectangular triangle. So this is also 90 degrees. And so we know that this is 90. Now, if this is 90 and this is 90 minus phi divided by 2, this is 45 plus phi 2, because the sum must be 180. Okay? Or you can just either just believe me that this is 45 degrees plus phi 2 divided by 2. So if you plot your slip planes, that they refers to all circles, because you have plenty of circles like that. Anytime you increase your vertical stress, increasing your Z, you have a lot of circles, you have different planes. So all these parts becomes failed along these slip planes, and then if the wall moves laterally, the soil slides along these slip planes and move laterally, without further decreasing your horizontal stress, because this is the limit, the minimum value, possible value. Okay? But, of course, this is the ranking theory behind it. In a way, we have solved the problem. Under the ranking assumptions, we know how to calculate the active pressure. And it is relatively simple. We have just one further step. In the same way, you can, before this further step, let's also have a look at this ranking limit state of stress. This is the other circle. Now, I won't do it again on the blackboard. You have these slides, you have the other circle. The original planes move on the other side, because now the horizontal stress is the major principal stress, so the other angle is 45 degrees minus phi divided by 2, and so you have the slip planes inclined like that, and you have that Kp is that value. So Kp, if you have sigma p, Kp, in passing conditions times sigma v naught. And you find out that Kp is 1 plus the sine of phi divided by 1 minus the sine of phi. And it is easy to check that according to ranking theory, which is of course very simplified because reality is not exactly like that, but this is exactly the inverse of 1 Ka. So in other terms, you can also say that Ka times Kp is equal to 1. For a phi equal to 30 degrees, you can see that this is 1/3 and Kp is 3. So it's 10 times greater than Ka. The horizontal stress is much greater, the passive horizontal stress is much greater than the active pressure. But they are used in two totally separate conditions, according to opposite load paths. Okay? Now, so if you have a look at these two slides, which are, if you want, one the opposite to the other, but referring to totally different load path conditions, then you can end up with the expressions which I have tried to derive at the blackboard with you today. Now, just one thing. Now, of course, we will skip the Coulomb theory and everything else in this presentation. Just there is one more thing that is not in this slide. You might have a limit line which is like that. So you have a cohesion C dash which is not 0. So in this situation, the Moore Coulomb criterion is tau C prime plus sigma prime tangent of phi. Okay, so you might have a circle which is tangent to this line. Let's put in green, for example. So you will have this circle which it will be like that. Okay, so you will still have a circle which is tangent, which is fully defined, but this geometrical construction will be slightly different because you cannot write that this is exactly the same sum as we have seen written before. So if you go through this, and I won't do it, so you have to believe me, your expression of sigma active will be Ka sigma dash V naught minus twice the cohesion multiplied by the square root of Ka. Okay? So in fact, if you have no cohesion, this term is not there, and you end up with the same expression that we found before. So if you have some cohesion in your soil, you have to add this constant term. Actually, you have to add, but there is a minus here, so you have to subtract 2c prime the square root of Ka. This becomes from another similar geometrical construction made in this way, which can skip. Okay, and if you have, and if you want to write sigma, the passive horizontal stress, you will write Kp sigma V naught, and this is the expression for a cohesionless soil. And in this case, you have to sum 2c prime the square root of Kp. So you have an additional term if you have a soil with cohesion. Everything stays the same, no different. Everything we have seen is exactly the same. The only thing is that, for example, this graph will not be exactly like that. But since you have this constant additional term, your graph will appear like that. Okay? And this is 2c prime square root of Ka. So everything is somehow moved, translated of this constant value.
And of course, this is a better situation, because if you consider that this is negative, and if you make the integral of this plot, you find the resultant, you will see that in presence of cohesion, the overall active pressure is less than for a cohesionless soil. Of course, this depends also on Ka, and Ka is a function of phi. But typically, if you have this term, the cohesion will tend to reduce the active pressure. And it might be that your cohesion is high, is very high, that this is equivalent to this, and the resultant is zero, because this compensates this. So for a soil which is with a strong cohesion, the active pressure is much less. In principle, if this is equivalent to this, equal to this, the resultant is zero. So in principle, you cannot build any wall, because the horizontal passive force is zero. And in fact, why can you excavate sometimes soils? You excavate, you see, in urban areas or any time, you can excavate, and the soil will be able to stand up, even vertically, with no vertical wall. No wall at all. Because, why? Because the resultant is zero. There is no pressure, which is a good thing. And you will determine what is called the critical height of the vertical excavation, and you will know how high can be your excavation before you need some structure, some retaining structure. But for a cohesionless soil, you don't have this, you just have a triangular, so even a 1 meter or a 1 centimeter will have some wall, and you will have some horizontal pressure, and you need some wall. So try to build, you are at the beach, try to build a vertical wall, try to excavate in the dry sand a vertical wall, and you will not be able to make it stand up on its own. Even 1 centimeter of sand, the sand will fall down, okay, because there is no cohesion. So that's the reason, that's the difference. But, as I said, the application of the Rankine limit states of stress to the design of earth-retaining structures is will be taken by Professor Marchi. We will use the same Rankine limiting states of stress once we have understood when it is active and when it is passive. This was the objective, the aim of this first part. But we want to use this Rankine limiting states of stress to define the bearing capacity of a shallow foundation. So let's abandon this presentation and let's start with another one which I have to upload. Now it is 10:30, so I will avoid the break, steal from you the break this morning. Try to probably end a little earlier, but there is no reason of having a break right now. Let me upload this presentation. Bearing capacity of shallow footings. Now, let's talk about foundations now. Foundations are the typical geotechnical structure. Very basic one. Any structure, say any building, anything has to bed to rest on soil. And the connection between the structure and the soil is a foundation. And so foundation is the connecting element. This can be made of different type of structure. If it is a very simple enlargement of your wall, of your columns, of your wall, of the building, it is called footing. So you can call it footing as a type of foundation. But you see very clearly the foundation is the connecting element between the structure and the soil. It is also, if you wish, the connection between structural engineering and geotechnical engineering, if the two engineering were to separate different things, instead of two parts of the same technical competence of an engineer, of a civil engineer. Civil engineer must know how to design the structure and how to design the foundation. But remember, the foundation is not just a structural element. The actions, the stresses on the foundation depends on the structure above and on the soil below. So as an engineer, you have to consider the soil as an engineering material in relation to this connecting element. So the foundation is the part of a structure which transmits loads directly to the underlying soil. Now, typically, the foundation, if it is shallow, just below the ground surface, is larger than the wall or the pillar, the column of your structure. Because one thing is concrete and stresses that the concrete is able to sustain. Another thing is the soil, which can sustain stresses, tangential stresses. Now we know that, but typically the strength of the soil is much less than concrete or other steel or other construction materials. So that's why you need to enlarge, increase your section, reduce stresses, and allow that these stresses are supported by the soil. Because if you transmit the same stresses of the concrete into the soil will fail, will reach the failure, because there is a failure limit in the soil, and you have not to reach it. So essentially, you have to design a foundation in order not to reach the limit of your soil. And to do that, you have to calculate the bearing capacity of your foundation. And this is the object of this presentation. We have to separate, we have to understand that you might have essentially two types of foundation, shallow or deep, with a question mark, because you have to decide which is suitable for your structure. Shallow foundations are simpler, are cheaper, are easier to design, so we will typically try to design a shallow foundation. Anytime it is possible to use a shallow foundation, you will go for shallow foundation. What is a shallow foundation? It is what you can see on the left-hand side of this slide. According to Terzaghi, as long as the depth of bedding of your foundation, that you can see df, is the depth below the ground surface at which you find your foundation, divided by the characteristic breadth of your footing, d over b, is less than 2.5. But this is just a geometrical definition. On the other side, you might have a deep foundation, which is typically a pile. You might have heard that you have piles under your buildings, under your constructions, And a deep foundation can be also of other types, but the main, by far, the main type of deep foundation is pile. Single pile or a group of pile, large diameter pile, square section pile, typically circular section pile foundations. So a deep foundation is when df, which is the distance between the ground surface and the bottom of your foundation, so in this case can be also thought as the length of the pile, df divided by b, where b is this time the diameter of your pile, which is the breadth of your footing, is greater than 15. Now, of course, what happens between 2.5 and 15? You have a moderately deep foundation. You have something in between, something intermediate. Now, irrespective of this geometrical distinction, a shallow foundation mainly behaves because of the stresses transmitted at the bottom of your foundation. You see all these arrows here. Here, this is the stresses which are transmitted by the superstructure to the soil. And the way it interacts with the soil is through the bottom of the foundation. We neglect what happens along the sides of the foundation, which is very small. Typically the soil around is a remolded soil, so we typically neglect the lateral interaction between the foundation and the soil. Whereas for a deep foundation, a pile, you have both mechanisms acting. You have your stresses transmitted at the tip of the pile, at the base of the pile, but you have as well, and most of the time above all, you have all the stresses, tangential stresses, transmitted along the lateral sides of your pile, along the shaft of your foundation. And most of the time you design your pile according to that shaft resistance. You can neglect, or you will use the bottom, the tip resistance for, you will see when we go into the details of the design of a pile. But essentially these are the two mechanisms that you have for a deep foundation, whereas for a shallow foundation what happens along the sides is typically neglected, is not relevant. So that's the main difference between a shallow and a deep. If you have something in between, you might have that both mechanisms are important and you have to consider both, but essentially a shallow foundation, irrespective of this geometrical ratio, is when you have only the bottom way of interacting with the structure. Now, there are several shallow foundation types. I'm sure you are familiar with the single foundation that you see can be a square foundation, which is just an enlargement of your column. As I said, this is a plan view. You have the column and you have to enlarge in order to decrease the stresses transmitted to the soil. Now, of course, if you have different columns, you might have different, might have a unique enlargement. You have single footing, which is not square, can be rectangular or can be any shape. This very much depends on the shape of your structure and the distribution of the applied loads. You can have also a bearing wall, and that in that case you need not just a single footing, but a strip footing, which is all along the load-bearing wall with, once again, an enlargement of the bearing wall to your footing, which is large B. Okay. Now, the footing itself is a structural element,
and must be designed as a structural element. So you have to verify the concrete stresses, the steel stresses, you have to verify. And this is nothing different from the design of any other structural element of your building, of your superstructure. Now the only thing is that the stresses acting on the footing comes from the soil. The load comes from the superstructure, but then there is the reaction, the contact pressure of the soil. And so you have to design this structural element once you have determined the contact pressure of the soil. And in fact, you see that you have this steel element, which is typically at the bottom of your foundation, because the foundation will be pushed by the contact pressure from the, say, upwards. We do not deal with the design of the structural elements. We are concerned on what happens to the soil. Once we know what happens to the soil, we will be able to know also the contact pressure and to design the structural elements as all the other structural elements of your building. Okay? So, what is the geotechnical design of shallow foundations? An important task for a geotechnical engineering, the design of the foundation, is to use the knowledge of the properties of soil and their response to loading. So once again, we are now focusing on the soil. The foundation is just a structural transmitting actions to the soil. Our focus is the soil, what happens to the soil. And if you look at the left-hand side figure, you can see that if this is a foundation loading, this is typically what we expect and what we have described last week as a foundation loading. So you typically increase the vertical stress and you do not increase the horizontal stress. But if you consider that this is a possible slip line, a possible failure line along which you reach failure, and so you have sliding on the soil and you have failure of the soil, then you can see that there are other soil elements that will undergo different stress path. And for example, if you have this element, you see this is more typical like a simple shear of your soil. And if you look at the soil which is at the side of the footing, this is more typical like something passive, because you have no increase vertical, but you have increase horizontal. So that's why we started from this type of discussion this morning, because under your foundation you develop different possible stress path which corresponds to different soil elements. Now we have to put now all together in order to define what is a possible mechanism of the soil below your foundation. Okay, you apply your foundation and you have two things. A foundation must satisfy two limit state conditions. The foundation must not collapse or become unstable under any conceivable loading. So typically we have always to design against ultimate limit state. What is the possible geotechnical ultimate limit state? Soil failure. So let's think, for example, that you apply the load to your foundation and then you measure the settlement of your foundation. So you have your foundation and you increase the load. You increase the load, you increase the load, and of course the soil below your foundation will tend to settle, to move down because of the applied load, unless the soil is perfectly rigid, and it is never perfectly rigid.
Okay, so you have this trend. You increase your load, you increase your settlement. At some stage, the soil will no longer able to sustain the increasing load and will fail. And you can see that failure means that you have continuous settlement of your foundation without increasing the load. So somehow you lose your foundation because continues go down without increasing your load. Now this is not realistic. Of course, we know that the foundation at some stage will stop, but once you reach very large settlements, you consider that the soil has failed, that you have reached the bearing capacity of your foundation. The bearing capacity is the maximum capacity of your foundation. But the bearing capacity of your foundation does not depend on your foundation. Depends on the soil beneath your foundation. So we should talk in terms of bearing capacity of the soil and of your foundation, because as you will see, the bearing capacity, the limit applied load, depends on the two things, both the foundation and the soil beneath it. But of course, a proper design of a shallow foundation must consider also the serviceability limit state. Because once we know that we will be kept far from failure, still we have to check that under the design, the exercise, the working loads, the settlement of the structure must be within tolerable limits. Okay? I have to guarantee that the soil does not fail, but if the settlement under my working load, the settlement is too large, this might prevent the serviceability of the structure. You might develop cracks, you might have all sorts of problems in the superstructure if the foundations move too much. In principle, you might have also a failure of the structure if you have differential settlements of your footing excessive. And so you can reach ultimate limit state of the structure because of an excessive settlement of the foundations. So the geotechnical design must guarantee your foundation from ultimate limit state and serviceability limit state. Now, if you look at this possible applied load settlement curve, this means that I have to stay away from the bearing limit, but I have to guarantee that under the working load, the resulting actual settlement, which as I said will never be zero unless the soil is perfectly rigid, but the actual settlement is small enough, is tolerable for the structure. This is a bit more tricky to define, because what is tolerable? This depends also on the superstructure. So there is not a specific limit and depends on many aspects. And we will go a little bit more into the details of the settlements. We will deal with both things, bearing capacity and settlements. Now, in many cases, the need to limit the settlements to tolerable values represents a more restrictive design requirement, and the settlement computations governs the design of shallow foundation. So you still have to guarantee that the bearing capacity is enough, but it is not what governs the design. Typically, your design is governed by limiting the actual settlements under working loads. Okay? Now, one final point in this slide, which is important to remember, that the foundation level should be below the depth, which is subjected to forced action. But if we go a little bit back to the previous slide, you see we are saying that depth of your shallow foundation is almost never zero. Your foundation is not bedded on top of the ground.
First, because the surface, the ground surface, is typically remolded, but mainly because it is subjected to climate variations. The soil can move just because there is a water content variation during season, for example, from winter to summer, and the soil will tend to shrink or expand because of water content variations. So you have to put your foundation at a depth which is far from these seasonal variations, which in cold climates can be also a frost action, because in winter the soil can become frost, can freeze, can be relatively deep if you have additional vegetation, which can take your seasonal variations, water content variations deeper. And this is something which is have to be considered very carefully, because most of the problems that you can find are not related to a matter of bearing capacity or excessive working loads. You have cracks on your building because the foundation is moving, because the soil is moving itself, just because you have selected a DF, a foundation depth, which is too small. Now, an important thing you have seen. Let me. Okay. Let's say this is our final slide for today. In the previous slide, we have this was a qualitative diagram to separate ultimate limit state from serviceability limit state. And I said once you reach an undefined settlement, you have reached bearing capacity, bearing resistance. In reality, this is the graph that you get. So your curve never reach a horizontal limit. You always increase your load while you increase the settlement. So typically, in order to define failure, we are not able to find a limit, but we have to define a limit to the load, but we have to define a limit to the maximum settlements, by which we assume that the soil has failed. Where does this plot come from? If you see, you have a dimensionless settlement, W is the vertical movement of your foundation, which is divided by your footing. In this case, it was a circular footing, so a diameter D. So let's assume that you have a circular footing, say 2 meters diameter. If you think 0.2 is 20% of 2 meters is 40 centimeters. 40 centimeters is clearly a very large settlement and typically not tolerated by the superstructure. And in the vertical axis you have Q, and you have the vertical, you have the applied settlement. Now, it's very difficult to run a test. This is an experimental curve. It was not analytically or numerically determined. This is what we measured once you increase the load of a settlement or of a foundation, and you measure the settlement. Now, in order to reach those very high stresses, and in order to reach these very high foundation settlements, you have to build a setup in the field which is quite big, typically very difficult, very expensive to realize. How was this experimental curve determined? Therefore, this was done in a centrifuge. Now, I don't know if you are familiar with a centrifuge.
a geotechnical centrifuge, which is not exactly like a washing machine you have at home, which is a centrifuge, and it is basically the same principle. Once you spin rapidly, you generate a centrifugal force, which is normal to the circle that you are running, that you are spinning. Okay, so in other terms, you put your foundation bedded on your soil on a relatively small sample, and you spin the whole model rather quickly around. So you generate a circular force, a centrifugal force, and you increase, or what you enhance, as we are used to saying, your gravitational field. Okay? So you keep spinning all the time, and you generate a stress field in the soil which is increased, enhanced. Why is it important? I spent just a couple of minutes explaining the centrifuge, which is not necessarily related to foundations, but it is important for in soil mechanics, in geotechnical physical experiments. Now you know that everything in geotechnical engineering, in the soil behavior, is depending on the stress level. We have seen, for example, the strength depends on the mole Coulomb. The stiffness of the soil depends on the stress, effective stresses. Everything, all the soil properties depends on stresses, soil stresses. So you have to generate, once you want to run a physical experiment, like loading a foundation, you need to replicate in the laboratory, at a small scale, you have to replicate the same stress field. If I build a caisson like this, and I fill this caisson with sand, then I put a small footing here, I can load it, and I can measure the settlement. This is like a small-scale foundation. But the stress field inside here, if this is, 1 meter, you can't do a model which is much larger than 1 meter. The stress field is not the same that you have at 10 meters or 100 meters or whatever. The stress field that is in reality. Okay? And the stress, we know, increases linearly with depth. So you have gamma dash times z. Now, if you cannot increase z because you are limited in the size of your model, you can increase gamma. How can you increase gamma? The soil, because gamma is the density of the soil, rho times g, which is the gravitational force under typical circumstances, okay? 9 times 0.81 meter per square second. This is our gravitational field. So the density is typically the same. You have to reproduce the same density that you want to use, that you have in the field, but you can increase g. So by spinning and generating this centrifugal force, you can reach g, which are sometimes greater as 100 times g. Okay? So this means that if you are there, you are under 100 times your weight, which is not nice and certainly not bearable for a human being, but for the soil, yes. And this will generate a gravitational field which is still distributed linearly, because it is like that, increasing linearly with z, but increasing with a slope which is 100 times the normal gravitational field. And this means that 1 meter will be 100 meters. The same stresses that I have under 100 meters. So I don't need really going that depth. Probably 20 meters is enough. So 20 centimeters of sample is enough to simulate a 20 meters thickness. So you see, centrifuge is great to me. It's quite complicated. You have to load your footing, still keeping spinning, and so you have to measure settlement to apply any load while you are spinning, and it is quite a sophisticated piece of equipment, quite an expensive piece of equipment. Only few laboratories can have a centrifuge. In Italy we have only one centrifuge in a laboratory in Bergamo, and it's not the typical piece of equipment that you can have in a laboratory. But once you want to simulate complex problems, this is not that complicated, but still not easy to reproduce in a standard laboratory, but even more complicated than in geotechnical engineering. You have to use a centrifuge. Okay, so you have to be you must spend some money to run this kind of test. So this was just a little deviation from our. So what you get here is exactly what you would get under a real foundation. In this case, this was a very small foundation, only 5 centimeters diameter, but corresponding to a sort of 5 meters or 2.5 meters. I think these tests were run under 50G, so you have to multiply all dimensions by 50. So this is what you would expect from a real foundation once you get to higher settlements. And you see, you never reach a horizontal asymptote, but this is what you should keep in mind when you design a foundation. Now, of course, tomorrow we will continue, and we will at last going into the details of a shallow foundation design. Okay, so see you tomorrow.